Yeah, I'm not sure why I volunteered. I thought it'd be good to break out of my shell and get to know everyone better. But I just found out that this is recorded and going on YouTube. So yeah, I probably would have done some things differently, but it's okay. So yeah, I don't really know what I'm doing because I've only seen 2 of these. So I'm just going to talk for 15 minutes about something that I've been interested in, particularly computer security, and we'll see how it goes. And the images, I should have credited them. But anyways, so the name of the talk is Taste the Salty Rainbow. And this is just a brief hashed together talk. It's about rainbow tables, which is a way to attack, well, I'll get into it in a second, but that's full of puns. By the end of the talk, you'll understand all the puns. Okay, so first I'm going to go over some background and motivation, because there's some personal reasons why I'm interested in this. But then I'm going to talk, there's not really enough time, so just really quickly to say what a hash function is and how it's used for password security. And then I'll talk about rainbow tables, and then finally get to our favorite spice. So again, this image will make sense by the end of the talk. But I've been thinking about this for like a month now, an image like this, and I put it together this morning, and I think it came out pretty well. Yeah, and again, you'll understand what all this means. It will be the last slide. So, but that's this is a rainbow. This is a rainbow lightsaber. This is a hacker, a reference to Anonymous or V for Vendetta, and a Sith Lord too. And then that's Luke Skywalker. This is a long salt shaker, and this is a classic salt shaker. So, okay. So background and motivation. So one primary goal is, when programming, you often probably have used hashing. If you studied computer science school, you probably studied it briefly. But when it comes to security, I found myself doing like encryption and other things, and I really had no idea how it was working or why I was doing it in particular. And so the goal is, I'm trying to learn more about this stuff, and obviously we all should, because we're all software developers, because you should be aware of security when you're designing things. Another thing was when I first met my wife, who was then just my girlfriend, she used to use like really short passwords that were just like a word followed by 2 numbers, and I used to always yell at her for that. But then when I started to think about it, I really didn't know why that was bad per se. And then recently, the DBags at Adobe were hacked, and my account information was pasted onto that Pastebin website with my hash password, my address, my account name, everything. And so, I didn't, obviously that's bad, but I didn't understand why it was that bad. So I wanted to learn, what can hackers do if they have your hashed password, because they don't have your actual password. And yeah, in Adobe, they should have given me free software, but they didn't. Okay, so a cryptographic hash function. A hash function basically takes some input, generally like a string, and then it computes a fixed length, typically represented as hexadecimal output, right? And so the idea is that it can be used for table lookups, a lot of things, but obviously it can also be used to obfuscate some information. So the red fox jumps over the blue dog. You apply the function, which has to do with number theory and all this cool stuff, and then you get out this long hexadecimal output. And so this is meaningless unless you can somehow reverse the process. But hash functions are designed such that they can't really be reversed in any feasible manner. So there's a number of algorithms around that, and it's obviously a huge thing in security. And so what I'm going to go over right now may be a little outdated, but the idea is that you should start from the beginning to understand and work your way up to the modern, more sophisticated encryption and hashing techniques. So password storage. So when it comes to passwords, suppose you have a website with users and you have usernames and passwords stored in a database. So someone could do, like, let's say, a SQL injection attack and dump your entire table of usernames and passwords. So if those passwords were stored in plain text, the attacker could then immediately log on everyone's accounts and do whatever they want willy-nilly. So the idea is that if you store people's passwords in their hashed form, the attacker, if they have this value, won't be able to log in because they don't know what the actual original password is. And so and it's a never-ending game of cat and mouse. There's so many ways to try to reverse the hash value. There's brute force. There's things called dictionary attacks. But what I want to talk about are rainbow tables because I think they're pretty cool. And yeah, so the problem is defined, I guess you want to say mathematically. So if f is a hashing function, so p is some set that contains all functions, and it maps passwords in this set to values in a hash set. So this contains, you can think of this as the image of the function. And so the problem is if we have a hashed value h, so that means h is in the set h, we want to find the value p such that the hash function evaluated at p gives us the hash value. In other words, we want to find the password. And some quick overview of some basic methods. There's brute force, so you can calculate the hash for every single password in the password set, which is huge. Let's say you want to find the hash values for every, let's say, password that's 5 characters long. I mean, that's 5 times 5 times 5, so forth. No, not much bigger than that, sorry. And then dictionary attack, so like my girlfriend, now wife, her password was a word followed by 2 numbers. So dictionary attacks, you assume that there's people that have bad passwords, and then you make a list of all those bad passwords, like let's say common words followed by 2-digit numbers. And so it greatly reduces the size of the set P that you need to compute all the hash values for. And so then let's say you have a database of all the hashed passwords. You can simultaneously try to find all the bad passwords that are easy to crack. But of course, yeah, I'm not going to go over big O notation and stuff, but the size of, let's say, passwords that are 7 characters long, P is going to be a huge, enormous set. Because you can have numbers, letters, symbols. OK, so what rainbow tables are, they're a way to, and let me say one last thing. So the idea is you have a brute force attack, which requires not only a lot of computation, but if you, let's say, want to store all the hashed values, I mean, that's a huge data set. So rainbow tables are a way to optimize this trade-off between computation time and storage space. And so the idea is that you pre-compute a table that's small relatively compared to if you did a brute force attack. And then you can use a lookup method that takes computation time, but a lot, if you trade it off with the space required, there's like some golden area that you can find. And this, I'll get a little bit more into this. So yeah, you pre-compute hashes for a class of passwords. So let's say you get a database of everyone's hash passwords, and you want to find you want to find passwords. Let's just assume, make a lot of assumptions here, a lot of hand wavings. Let's say we know all the passwords are only 5 characters long. So we know then what the space of all passwords is. And so we can pre-compute way ahead of time all the hashes for all those passwords. But instead of storing all those hashes in a gigantic database or table, we can store just a very limited set, but in such a way that we can still look them up in a feasible amount of time. And so the method is what's called known as chaining, where you generate a set of random passwords from whatever the password set is that you want to crack. And then for each password, you generate a chain of length k. So remember what k is. This represents the length of the chains. And then you save only the first and last entry of each chain. So suppose there's only 100 passwords in that space, which is a really small number, but you want to generate k is equal to 10. So instead of storing 100 hash values, you'd only have to store 10, because you have 10 chains of length 10, so you only have 10 passwords that you store. And so that's a whole order of magnitude smaller storage size. Obviously, in the real world, they'd be much bigger. We're talking like gigabytes, terabytes, but yeah. So how we construct them. So it's this may be a little confusing at first, especially since we don't have much time, but and going back really fast. So from here on out, the function f represents our hash function. So, and k represents the length of the chains. So to make these chains, we actually define a reverse mapping, g. So h is, remember, the set of all the hashes, that space, and p is the set of all passwords. So we define a function that maps hash values to possible passwords. And note that this is not an inverse of f. And it's constructed in such a way that given a hash value, you get back a possible password value that belongs to the set P. But it's we could spend a whole hour talking about how G is constructed. So an example would be you have a hash value. You take the last 4 characters of it if you want to find 4 character long passwords. That's just a very simple example, but there's a whole theory that goes into constructing G. And so this is an example of how we construct a chain. So we pick a random password in the set of all passwords, and then we generate a chain of length k by first applying the hash function. So we get a hash value, and then we apply the reverse mapping. And so you have the hash value, evaluate G at that value, and you get back something that's in P. But again, note that G is not the inverse of F, because it's just an arbitrary mapping. And so then we get back a password, and then we find its hash value again, and then we take that hash value and apply G again and get back another password. And we do that until we get k hash values. And so you continue to the chain. And so suppose we only want a chain of length, let's say 1, 2, so of length 3. So, 1, okay. So this, there should be one more F here. So you always end the chain on a hashed value. And so what you do is you save the original randomly selected password P. And then suppose this isn't here, and then we pick the final hash value in the chain. So you don't store any of the intermediate values. You just store the original password and the final hash value. So again, reducing the storage size. So why is that even helpful? Well, it's pretty interesting, whoever came up with this. And it's actually based on a method that in a paper, and I forgot to include the citation, but I'll get that for you. OK, so how do we use this to look up passwords given a hashed value? So if H is some hashed value that we somehow stole, we want to start generating the chain beginning at the password given by the reverse mapping. So the notation that I'm going to use here is the subscript represents the index of the step in the chain. So in other words, P1 would be the first password value generated by the function G. And then H1 would denote the first hash value that we get from that. So you can do this right up to k times. And the idea is that at each step, when you find the hash value, you look in your rainbow table and see if it exists in the second column of the final hash values. And so suppose we have a hit. So suppose we calculate the second hash value, and it exists in the rainbow table at like some arbitrary row. Then the idea is that we know then that row in the rainbow table, even though the chain, we don't have that chain because we didn't save it, we know that the password should exist in that chain somewhere. And so what we do then is, so if we have a hit, we regenerate that chain again that we originally did a long time ago when we made the table. And as you regenerate that chain, you're eventually going to find a password value that gives you your hash value, because your hash value is in that chain. And so what this does is you don't have to do a brute force attack. You really are only checking for a single entry. You only have to do up to k computations, 2 times k computations, right? You have to do k hashing, k reverse hashing values. And then you have to look up, at each hash value, you have to look up the second column of the rainbow table. And so that's where the value k comes into play, because the larger k is, the fewer lookups you have to do for each hash value, but also the more computations you have to do for each chain, because it's a longer chain. So you can find, there's theory that goes into that, try to find a good golden value that trades off speed versus storage space. On the other hand, suppose we want to know if, suppose again, capital P is the set of all 4-character long passwords. It'd also be helpful to know if the password that we're looking for isn't 4 characters. And so if after k steps, none of the hashed values exist in the rainbow table, then we can conclude, star caveat, take note, that the password is not in that set of passwords. So pay attention to these 2 stars. So notes to the previous slide. So when I say we know the password must be in the chain, when we have a hit, this assumes there's no collisions, which I'll define in a second. And then the second caveat is that when we say we can conclude the password is not in our predefined set P, this has a number of assumptions. First of all, the assumption is that the rainbow table covers all the values in P, which is difficult because the function G, again, it takes a hash value and gives you back a password in P. You can't really know for sure that every value in P is going to be covered in the table. So it's not always possible to know that for sure. And then, and again, this is where how G is defined is important. So what is a collision? So a collision is where the hash functions are carefully constructed so that you don't have collisions. It's like 1 in a billion chance, right? So the problem is G is not a hash function. It's just a function that we make that has a much higher probability of collisions. In fact, you're almost guaranteed to get collisions because it's not a hash function. And so a collision is defined as, let the superscript denote the number, the index of the row, of the chain, I mean, so like the row in the table. And let the subscript, again, denote the step in the chain. So a collision would be where you have two different rows in the rainbow table, 2 different chains that don't have the same starting password, but where at some point along the chain, they both have hash values that give us the same passwords when the G functions evaluated them. So that would be a collision. And so what happens is that chain N and chain M, they have different starting password values, but somewhere along the line, they're going to coincide and you have redundancy because now you have you get led down the wrong path. So suppose, I wish I had a marker board to illustrate this. So you have, let's say you're doing a lookup, and after 3 computations, you think you find the hash values in the rainbow table. Well, that can be misleading if you have a collision, because that hash value that you found may instead be an intermediate value in another chain. And so what happens there is that when you go to when you have the hit in the rainbow table and you recompute that whole chain, you won't find your original hash value. And so then you have to go back and keep looking again. And so it adds more computation time, redundancy. Another effect is that, again, when you have overlapping, you don't cover as many passwords. So you don't have a, you can't guarantee that you cover the whole space of passwords you're hoping to crack. Now, so the last thing I'll go over is an effective approach to deal with collisions is where you now, if you have k steps in your chain, you define k different G functions, reverse mapping functions. And so now a collision can only happen in the same exact step. So it's much less likely. Now the trade-off is that you have increased computation, because when you calculate the chain, you have to do it k times, because when you have a hashed value h, you have to see, okay, what if it's the first hash value in the chain, and then you start with G1, do G2, so forth, potentially up to k. And okay, what if it's the second value in the chain, then you have to start with G2 on it. And so you'll have, k plus k minus 1 and so forth. So you have to do more computations, but you have less redundancy, like almost no collisions, and so overall it's more effective. Okay, so I should probably hurry up. It's been a long time. Here's an example from Wikipedia of multiple reduction functions. So you have an original password, apply the reverse function, get a hash, apply the hash function, get a hash, apply the reverse function, get another password, and then now this is a different function from R1 and so forth. So, and that's my notice to stop talking. Okay, so really quickly, salt. So salt, they're good for margaritas, but they're also good for pwning rainbow table attacks. So I used to use salts, when programming, and I never knew why, really. And so I wanted to learn why. And so here's where they come from. So when you suppose that you use a hashing, the hashing function is known, and so the hacker gets a table of all the hashed password values. What if when you generate the password and store it in the database, you also generate a random string or random array of bytes that's unique, assuming your random number generator is strong for each password. And so in the database, you store a hashed value where you concatenate the password, the plain text password, with this random array of bytes. And so then in the database, you store not only this hash value, but also the salt value. And you can also do like double hashing, which will, the rainbow tables will take twice as long to generate. And so the idea is that, so what if the hacker gets the salt value? Because that's something I never understood, is like, why don't I try to hide the salt value in my programs? And even though you should, the reason why it doesn't really matter per se is the whole idea is that if you have a really long salt, like let's say, 256 bytes. I don't know, I'm not sure what the standard is nowadays. But if you have a long enough salt, the hacker is going to have to, for each individual password in the database, generate a unique rainbow table. And so that takes a long time, and then they're going to have to do the lookup. So in other words, if you have a password that's 40 characters long, and the company has good security practices and they use SALT, unlike some earlier Microsoft software, then you can, it would take impossible until we get quantum computers. You'd never be able to find the original password. And so that's how SALT works. So SALT is very effective against rainbow tables. That's why we use it. And the conclusion is that it's too much time to cover in 15 minutes, but I think I did 20. This is why longer passwords are better. So I think it's like up to 7 passwords, it's feasible, with enough time and computational power to generate rainbow tables. But once you get to 8, length passwords, we're really talking, you really have to spend a lot of time. And my colleague Ben, where is he? There he goes. Yeah, so I learned that he uses 40 character long passwords. So yeah, don't try to hack him. You'll never be able to do it. So and rainbow tables, again, they're like a really small part of security. They may not even be really effective anymore. But you can find rainbow tables readily available for different old Microsoft software and Unix systems. But what I like about them is they kind of give a historical context as to where SALT came from. And at the end of the day, hacking is just a game of cat and mouse. And so rainbow tables are just one fun, interesting example of how that, how modern security came to be. And then one last time, I've been thinking about this picture for a while, so I really just wanted an excuse to show people it because I thought it was really clever. And that's it. Thank you.